Welcome to Unit 3, Part 2, more on processes. So today we're going to talk about system schedulers and operations on processes. So in your system, you have a bunch of different queues, and there's the job queue, which is the set of all processes that are active in the system. That means all of those that have the operating system has PCBs on. And then you'll have the ready queue. These are all of those processes that are active and are actually ready to go on the CPU. So your operating system is keeping track of all of these processes, but there are those that are actually ready and waiting to get onto the CPU. And then you have device queues, and these are all those processes that are blocked or are in I/O waiting for a device or waiting for another process. So your processes will migrate between these different queues. They will be ready for the CPU, using the CPU, or they will be waiting to use a device or waiting for the result from a other process or something like that. And so you want to switch your processes very quickly and switch between them and get all of your tasks done. And that's part of the management of the operating system. And the operating system will have a set of different schedulers to help with these tasks. And the first scheduler is a schedule that all operating systems have, and it's called the short-term scheduler or the CPU scheduler. And this selects from those processes that are in the ready state which processes are going to get next on the CPU. And we will be doing exercises on CPU scheduling and learn a lot of different CPU scheduling algorithms. So all operating systems, even if they schedule the processes in first come, first serve order, do have a CPU scheduler. Then some operating systems will add an additional unit called the long-term scheduler. And this is the scheduler that makes the decision on whether or not to admit processes into the system. So again, remember that when a program goes from an inactive entity to a process, the operating system will create a PCB and will make a decision on whether or not it can admit it. If you don't have a long-term scheduler, then the process will just, if there's no resources, it cannot be admitted. If you have a long-term scheduler, the long-term scheduler may be able to terminate some of those processes that are taking up resources in order to admit new processes in. So that could be one way to deal with the unlimited resources that are available. Another way to deal with it, and the long-term scheduler will control the degree of multiprogramming. If you remember that the degree of multiprogramming means the number of active processes in your system. The medium-term scheduler is another unit that can be added, and this one will then take on the role of swapping. So instead of terminating processes in order to add new tasks, this can control the degree of multiprogramming by swapping those processes that are taking up memory and taking up resources, swap them onto a backing store, which you have to have a relationship with your hard disk, swap the entire process onto a backing store, or just swap pages or segments or portions of a process. But either way, this is part of the task of the medium-term scheduler. And between the medium-term scheduler and the long-term scheduler, those are the ones that control the degree of multiprogramming. So here is the diagram of the medium-term scheduler or swapping. This is the state diagram. If you remember, the processes would either be in the state of ready, which is waiting for the CPU, running, which is executing, or blocked, which is in or out in I/O. Now, some processes might be swapped. So I've added these other states because a process could be ready for the CPU, but it's ready for the CPU, but maybe it's taking up the resources that are needed for more important tasks or some other tasks, so it could be ready swapped. Or while it's out in I/O, blocked and out in I/O, it might be swapped out. So this is just some added states to the other state diagram that includes the swapping or medium-term scheduler. So you can each process, when a program becomes a process, there are two different ways to define a process. You can define a process as either an I/O bound process. That means it's a process that spends more time blocked in device queues in I/O, not on the CPU. So it has shorter CPU bursts and longer I/O times. Or you could have a more CPU bound process which has longer CPU bursts and less I/O times. So the idea to have a good in the control of the degree of multi-program is to have a good mix of CPU bound processes and I/O bound processes so that you can keep your tasks and your throughput and all of your system can get a lot of work done, because that's the goal of the system, is to get the work done. And now I want to define what a context switch is. A context switch is when you change the CPU from one process to another. So again, if you have one CPU or you have two CPUs or two cores, when a process is on there, whether it goes to I/O or gets interrupted and goes back to the ready queue, you want to be able to reload it where it stopped. So a context switch happens when you save the current context of the process, that's all the information of the PCB, and load the context of the next process. And this is pure overhead because the operating system needs to use the resources in order to perform a context switch. The next thing we'll talk about are operations on processes. Processes are created, they're terminated, they block, they wake up, they can change their priority, and they can be dispatched onto the CPU. So when processes are created, generally you have a parent process that would create a child process, and you can make some policies about what happens when a parent creates a child process. A policy could be that a child shares the resources of the parent, or that the child has its own different set of resources. So then the mechanism would be how you allow the child to share the resources, or how you implement the system to have the child separated from the parent. And then you can make policies about whether parent and children can execute together, or if the parent has to block while the child executes. And each process, whether it's a parent or a child, will have a unique PCB and a unique identifier. And here is just a sample of a tree of processes where a parent and which children processes come off of which parents in Linux. In process termination, that means when a process is killed or terminated, they can be killed either voluntarily or involuntary. And processes are killed voluntarily by finishing their task and exiting normally. Or a process may kill itself voluntarily by having some type of error check in its code which says, if I don't find this file or assert that this doesn't happen or whatever, then it will kill itself. That's still even though it's sort of an error, it's still a voluntary, it voluntarily exits the system. A process can involuntarily be killed by trying to do something illegal like divide by zero or access memory, or it may be involuntarily killed by another process. Again, you could have some policies about process termination, which include, no orphans, or do you allow orphans? And an orphan is a process whose parent has been terminated. So in a future section, we will talk in more detail about interprocess communication, and I'm just reminding you that processes that work together need to communicate, and there's two ways they can either share memory or pass messages, and we will do more details on this in Unit 7. Thank you very much. That concludes Unit 3, the System Schedulers and Operations on Processes, and we'll see you next time.